Okay, in this section, we're going to look at oxidation reduction reactions or redox reactions. The goals are to determine oxidation numbers of elements in a compound and understand that these numbers represent the charge an atom has or appears to have when the electrons of the compound are counted according to a set of guidelines. Recognize common oxidizing and reducing agents. Identify oxidation reduction reactions, redox reactions. Identify the oxidizing and reducing agents and substances oxidized and reduced in the reaction, and write and balance equations for redox reactions. So, redox reactions. These are reactions that involve the transfer of electrons. And for terminology, you need to know that oxidized or oxidation mean the same thing. And it means the loss or losing of electrons. And a way to remember that oxidation is the loss of electrons is oil. Oxidation is loss. And if you are oxidized, you're the reducing agent, meaning you cause reduction. And what does reduced mean, or reduced or reduction? It means the gain of electrons. Reduction is gain, RIG, rig, oil rig. Whatever is reduced is the oxidizing agent. It causes oxidation. So let's take a look at oxidation numbers and see how they help us to understand what's going on. So these things are not really real. They just help us understand what is going on in a redox reaction. So I'm using ON for oxidation number. The oxidation number of atoms in pure elements is 0. So this sodium in pure sodium, the oxidation number is 0. Each chlorine in this molecule has an oxidation number of 0. We don't assign oxidation numbers to whole molecules or compounds or formulas. They get assigned to each atom in a substance. The oxidation number on monoatomic ions is the charge. So in sodium chloride, sodium is a monoatomic ion with a charge of +1, so its oxidation number is +1. Chlorine has a charge of -1, so its oxidation number is -1. Fluorine in compounds is -1. So if we have HF, the fluorine is a -1. If we have OF2, the fluorine is a -1 each. Now, you might wonder, why did I put a +1 here? And the answer is, well, the next rule, and these are kind of in order of importance. The hydrogen in compounds is +1, so this is a +1. Oxygen in compounds is usually a -2. It's not a -2 here. Here, if we take a look, this is a H2O. The oxygen's a -2. The hydrogen is a +1 each. Notice what all of those oxidation numbers add up to. H2O, +1, +1, -2 equals 0. Okay? Look at what these oxidation numbers add up to, 0. What do these oxidation numbers add up to? 0. Okay. So I'm going to skip to rule 7. The oxidation number in a compound, when you add them up, is 0. So take a look up here. Each fluorine is a -1. What does oxygen have to be? It has to be +2 to make this work. So it adds up to 0. 6, chlorine, bromine, iodine in compounds is usually -1. But these are in order of importance, okay? So you do them in this order. And lastly, the sum of the oxidation numbers in the compound is 0, and the sum of the oxidation numbers in the polyatomic ion is the charge on the ion. So let's do a little practice determining the oxidation number. So in aluminum oxide, we have aluminum +3, aluminum +3, oxygen -2, oxygen -2, and oxygen -2. So I'm going to write the oxidation number below the symbol of the element. The oxidation number here is +3, +3, -2, -2, -2. Or more simply, we could do something like this just to make our life a little easier. +3 each, -2 each. Okay, So phosphoric acid, H3PO4. We know that if we do these in order, we're going to do the hydrogen first, +1 each. Oxygen next, -2 each. And if we look at that H3, that's going to be +3 total. If we look at the O4, that's going to be -8 total, for a total of -5. So there's one phosphorus. What does its oxidation number have to be so that when we total all of the oxidation numbers, we get 0? +5. Now, for the sulfate, -2 each, so that's a total of -8. And the oxidation number on sulfur has to be such that when you add it to the -8, it's got to be -2, so +6. And here I can check it by doing this. This is a -2, -2, -2, -2. These are not charges, these are oxidation numbers. And all of these oxidation numbers have to add up to the charge of -2. So if we let S be the thing that we need to figure out, what is S going to be? S is equal to +6. A little bit of algebra. For the dichromate, I know that this has to be -2 each for -14. 2 of that -14 is accounted for here, so I can think about -12. So 2 of these have to add up to +12. So that would be +6 each. And let's check. 2 chromiums plus 7 oxygens is 2 times +6, should be -2, plus 7 times -2, should be -2. 12 minus 14 is -2, -2 is -2, it checks out. Let's look at this next one. Determine the oxidation number of each element in the following. So the oxygens are -2 each. So the bromine has to be a +5 for this to work out to be a -1. The oxygens are -2 each. So the copper. The carbon oxidation has to add up to 6 total, so +3. Fluorine, -1. Here, you might say, okay, we're going to do the hydrogen first because it comes before carbon, oxygen, the rest of those things. But this is not a hydrogen in a compound for that particular rule. A rule that comes before hydrogen is -1 or +1, a rule before that is monoatomic ions have an oxidation number equal to the charge. Well, this is ionic. How do I know? Metal, non-metal. So that means that this must be calcium 2+. So what do each of these hydrogens have to be? -1. So what is the oxidation number on the hydrogen? -1 each. The calcium, +2. So here I'm going to do the hydrogen first, +1 each. Oxygen, -2 each. So I've got +2 -8. This has got to be what? +6, so that it all adds up. And here, +1 -2 each. That adds up to a total of what? -8 + 1 is -7. So here, this has got to be a +6, so that the +6 plus -7 is -1. So I'm pretty good at this. You want to get to be as good as I am. So let's look at an oxidation number, oxidation reduction reaction. And let's see. And what I'm going to do is I'm going to show you how oxidation numbers help us decide what's going on. So we're supposed to see what's going on with the oxidation number and see what's going on here. So let's take a quick look here. So what's the oxidation number on this iron? +2 because it's a monoatomic ion. The oxygen is -2 each. And so that this has a -1 overall, this has to be a +7. Now, in H3O+, the hydrogens are +1 each, and the oxygen's -2, and that will end up with a charge of +1. Here we've got a +3. Here we've got a +2. And here we've got a +1 each and a -2. So if we take a look at each of these different elements in here, we can see that iron goes from a +2 to a +3. Manganese goes from a +7 to a +2. Hydrogen goes from a +1 to a +1. And oxygen goes from a -2 to a -2. So here, there's no change. Here, there is a change. And here's how it works. If the oxidation number decreases, so that arrow down means decreases. If the oxidation number decreases, then it's reduction. And if it is reduction, it means it got rigged. And if it got rigged, it means it gains electrons. And if it got reduced, then it's the oxidizing agent. It causes oxidation. And the reverse is true if the oxidation number increases. This is oxidation. Oil, O, oil, lose electrons. Notice one O in lose, not two. Two O's is loose, like a loose tooth. And if it loses electrons and it's oxidation, then it's the reducing agent. Remember, to reduce means to gain electrons. Well, if you're being oxidized and you're losing electrons, but the electron has to go somewhere, so that somewhere gets the electron and it gets reduced. So when you get oxidized, you're the reducing agent. So we can see that the oxidation numbers of these two elements change. I like to focus on the one where the oxidation number goes down first. So I'm going to say that for the manganese, when we go from a +7 to a +2, the oxidation number decreases. Decreases means reduced. We could say reduction also. Reduced means rig, which means gain electrons, which means it's the oxidizing agent. So essentially what's happening here is your manganese with a +7 charge is getting 5 electrons so that it can become manganese 2+. So you see, the manganese is gaining electrons. Now, what's happening with the iron? We go from a +2 to a +3, which means that the oxidation number increases, which is oxidized, or oil, lose electrons, and it's the reducing agent. So what's happening here is your iron 2+ is turning into iron 3+. So where do we add the electron into this equation to make it work? And it would be right here. So that -1 charge and the +3 charge, add it together and you get +2. So here we say that this guy is about to lose an electron. So this guy is about to be oxidized. Okay, so there you go. Which of the two following are redox reactions? Explain your answer in each case. and classify the remaining reaction. Okay, so 2 of these are redox reactions and 1 of them is not. So how do we go about doing this? Well, usually if it's a precipitation reaction, you're going to form a solid of some sort. So this might be a precipitation reaction, right? This is not, and this is not. Also, if it's an acid-base reaction, you should have an acid and you should have a base. Oh, there's an acid and a base. So this might be an acid-base reaction. If there's a redox reaction, you should have an oxidation number change of at least 1 element. So let's see if we can find that. And if we find 1 element where the oxidation number changes, we'll just stop and say, hey, that's a redox. What's the oxidation number of pure zinc? 0. How about zinc with a +2 charge? +2. This is a redox. So this is a redox because we have zinc turn into zinc 2+. And the only way this works is if we say 2 electrons plus zinc turn into, oops, wrong way. Zinc loses 2 electrons. So this is a redox. How about this one? Is this a redox? Well, this is a +2. Hydrogens are +1, oxygens are -2. +1, -2, +6, +2, -2, +6, +1, -2. I've given up writing the each. We just want to know what the oxidation number is on one of them. Did the oxidation number on zinc change? Nope. How about oxygen? Nope. How about hydrogen? Nope. How about sulfur? Nope. No change in oxidation numbers. So that means no transfer of electrons. So no redox. So what is this? This is an acid base. How do you know it's an acid base? Because it's got an acid and a base. So 2 of these are redox. This is clearly a redox. Let's see if that's true. Oxidation number on calcium, 0. Calcium hydroxide, +2 because that's an ion. So the oxidation number changes. Redox because the oxidation number on calcium changes. Okay? So if you want a quick and dirty way to look at each of these reactions and say, well, what might be the easiest way to classify them? 1, if you look at acid-base, you look for an acid and a base. Precipitation, you look for ionic, makes ionic. Aqueous solutions make an ionic solid. If you look for redox, let's see if we see something in common with these 2 redox reactions. And the answer is, look, a pure element. Look, a pure element. Look, a pure element. Often, pure element. But also a change in oxidation number. Now, why is it that pure elements often result in a change in oxidation number? Well, because if that pure element has an oxidation number of 0, and then it's in a compound, its oxidation in a compound won't be 0. So that's a change in oxidation number. And how about gas forming? You look for a gas. Okay. In the following, decide which reactant is oxidized and which is reduced. Designate the oxidizing agent and reducing agent. So let's assign oxidation numbers. This is 0 because that's pure oxygen, -2 for each oxygen, +4 for the carbon, -2, +1, +1, and these must be, whoops, -2 each. right? Because if that's a -2 for one of them, then it's -4 total. That's a +1 for each of them. That's a +4 total. -4 + 4 is 0. So if we take a look at the carbon, can you see that the carbon goes from -2 to +4? Is that an increase or decrease? That's an increase. Increase means oxidized, which means oil, which means lose electrons, which means reducing agent. Now, let's look at this oxygen. The oxygen goes from a 0 to a -2, or 0 to the -2. It doesn't matter. It's the same both ways. It goes from a 0 to a -2, which is a decrease, which means reduced, which means rig, which means gain electrons, which means it's the oxidizing agent. Wait, drop the pen. Oxygen is an oxidizing agent? Well, lo and behold, it certainly is. Okay. So let's assign redox numbers here. 0, 0, -1 for each. And since that adds up to -4, and there's only one silicon, the oxidation number here has to be +4. We can see that the silicon goes from 0 to +4, which is an increase, oxidized, oil, lose electrons, reducing agent. And here for the chlorine, the oxidation number goes from 0 to -1, which is definitely a decrease, decrease, reduced. Do you see how those go hand in hand? Decrease, reduced, rig, gain electrons, and oxidizing agent. And there you go. Turns out that a lot of common oxidizing agents are these Hunkelbriefs. All right, and that's the end of the redox section.